Okay, so I realized that actually when the scouts arrived here at 7 in the morning, they should have called back and said we could get to V from here at 1 in the afternoon, and I forgot to update that. So, and actually the people who are going to be walking until 2 in the afternoon were going along this edge, not along this edge. But I hope you can deal with this small error without me re-recording that, that chunk of the video. So now let's talk about how this is actually implemented. This is why I have two copies. So what's going to happen is you're going to start at S. So initially, your estimates for when your scouts will arrive at each vertex, at each other vertex apart from S, the estimate starts at infinity. And then you're going to update it and successively and refine it, refine the estimates. So first, you're going to look and say, okay, from S, I can reach U and X. So what you're going to do is take the, say, the distance to U is at most 10, at most. So this is why we put the 10 in red. And the distance to X is at most 5. So what we do is put those vertices in a priority queue with priorities 10 and 5. So put U10 and X5 in a priority queue. Okay, so that's like you start your scouts off, and then you wait until something happens. Okay? So that's going to the first thing that's going to happen is at the earliest time, when they get to the vertex with the lowest priority. So that's like extract min. Returns x5. So that's when your scouts arrive at x. Okay, so now that's the earliest anybody arrives at x. So this is when you make this move. So set distance to x to be 5. Now you put y, so you can get to y after 7 hours, so y7, and v14 in the priority queue. Now, U is already in the priority queue with priority 10, but now you can get to it earlier than 10, so you decrease U's priority to 8. So now this is now going to be 7. This is going to be 14. And this is going to be 8. Extract min returns, well, what is the next thing that happens in the morning? Your scouts arrive at Y. So returns Y7. So you set distance to Y to be 7. So this becomes blue. Now you can get to V. I missed this in the previous part. You decrease V's priority to 7 plus 6, 13. Okay, so this, I should have decreased that to 13. And you don't change S's priority because it had priority 0. It's already been visited. And so now you're going to extract the min. Returns U10, sorry, U8. So the distance here, you actually know it is now 8. And then you decrease V's priority to be 9. Because when your scouts arrive at U, they radio back and say, oh, look, we can see how we're going to arrive at V at 9 in the morning. So you think, okay, you update your estimates for when your scouts will first arrive at these places. And you say, okay, and then you extract min. Returns V9, set distance to V, to V9. So this becomes blue. So that's as I said, that's the algorithm. How would you do this with a priority queue? Well, yes. And if you do it with a normal priority queue, for every vertex and edge, when you get to the vertex, well, you do an extract min to get there, and then for every edge leaving it, you're going to update the priority of the edges in there. Actually, you can start out to make it so that it's always update the priority. You can insert everything with priority infinite, okay, except S, which has priority 0. and that makes it a bit easier to code. So you're going to have an update. You're going to have extract min for every vertex, and then you're going to have a decrease priority for every edge. Okay, so if you do it with a normal priority queue, extract min takes logarithmic time, and decrease priority takes logarithmic time. So this is going to take using, well, okay, what I should, if this is the vertex set, and this is the edge set, so it takes vertex plus size of the vertex set plus the size of the edge set times logarithmic time. You only have one priority in the priority one key in the priority queue for each vertex, so it's going to take log v. So frequently, this is going to be written as O n plus m log n. So that's with a normal priority queue, which we know how to do. And then there is a priority queue called Fibonacci heap, which decreasing the priority takes amortized constant time. And if you use that data structure, then you get O n log n plus m. Okay, so which is pretty good. So that's Dijkstra's algorithm. That's how you think about it, and that's how you could maybe discover it. This is how you can implement it. This is the analysis. Let's talk about why it's correct. Maybe I will pause it. Maybe I will put a break here because